it's a subtractor circuit, and constructing a half adder and extending the result to the full subtractor. The only confusing binary combination of subtraction, it's a 0 minus 1. In this operation, this 0 borrows from the next higher significant bit a 1 from here. In the sense, this operation has got a borrow, and when this is done, it's a 1 0 binary 2 minus 1, and so the difference will be 1, and this one with a borrow, we have to, the reader have to remember this one, 0 minus 1, because of the borrow, it has a borrow, and this becomes 2 minus 1, it's a 1. Alright, so a half subtractor has 2 inputs and 2 outputs, one showing the difference a minus b, and another indication whether we have a borrow for that during that operation or not. So a and b, it's a 0 0 combination, a difference and a borrow indication, borrow. 0 0, usual 0 minus 0, even the difference is 0, and we don't need a borrow in this case. The next second one, the confusing combination, 0 1, yeah, during this 0 1 the difference is 1, and this can be done only with a borrow, so we have a borrow in this case. 1 and 0, 1 minus 0, the difference is 1, and we don't need a borrow. 1 minus 1, the difference is 0, and still we don't need a borrow. And if you are an expert looking at this truth table, we can directly say that the difference can be obtained making use of exclusive OR gate, but still that has to be shown with a proof, making use of a K-map, like reducing, expression for D in terms of A and B and borrow in terms of A and B. So for a difference, making use of two variable K-map, difference D in terms of A and B, A and B over this side, 0 1 0 1, and let's check for what values of A and B we have 1 for difference. Here we have for a combination 0 and 1. Where is that 0 and 1? Here we have 0 and 1, we have a 1 over here. Another one for 1 0 combination, another one for 1 and 0 combination, and there isn't any possibility for reduction, K-map reduction. So D, difference D will be, this gives 0 1, this gives 0 1 plus, this gives 1 0, in a, like it's a bar B plus A B bar, which is exclusive OR operation between A and B. This is for the difference. And talking about for a borrow expression for a borrow, guys, straight away this one there isn't any possibility, and only one, straight away 1 single 1 for the combination 0 and 1, so borrow will be equal to this one. Even that comes over here, 0 1 combination. If it is for a borrow 0 1 combination over here, and no reduction, nothing, so this cell gives 0 1, which is A bar B. So implementing, this is for the difference and this is for the a borrow indication. And so making use of this expression for half adder, and the half adder, guys, remember this one, alright, 0 minus 1. For the 0 minus when 0 minus 1, we have a difference of 1 with a borrow 1. And for a half adder, we have two inputs A B, and giving it to exclusive OR gate, the output will be A exclusive OR B, which gives us the difference. And taking out the NOT of this one, this gives us A bar and this B, alright, A bar and this gives B, which is AND gate, and this A bar B, which is for the borrow. This is for the borrow, and making use of this result to implement the full subtractor. I'm sorry, I'm getting confused whether it's a adder or a subtractor. We are implementing full subtractor. This is a half subtractor, and implementing a full subtractor. Making use of two half adders is a general repeated question in the exam point of view. And before going for that, a substitution like A exclusive NOR B is A B plus A bar B bar, which is still A exclusive OR B with a bar, There is some substitution when we implement a full subtractor. Alright, so this, we can have a proof for this one. We can have, starting with A exclusive OR B, and the bar All right, so extending this one, A exclusive OR B is A B bar plus A bar B and that bar. Just expanding this one and we still have the bar. Making use of De Morgan's expansion, De Morgan's law, when we split this bar, this AND gate, I mean this OR gate becomes AND. Alright, this one, this AND gate becomes OR, this AND gate becomes OR, and A B bar as it is, here also A bar B as it is, then comes the bar, this one, splitting that bar according to De Morgan's, that one. Alright, we continue with the ANDs over here, and here once again this bar, making use of, once again we have a AND operation here which becomes OR operation over here, and we have that A B bar, here comes our bar. Alright, and over that side even we have an AND operation which becomes OR operation, and inside the braces we have A bar B and De Morgan's, that De Morgan's expansion. Guys, this gets cancelled, twice a bar, that gets cancelled, and finally we have A bar plus B into A plus B bar, and simple mathematical expansion for this one, A bar into A plus this A bar B bar plus this is AB plus B into B bar. Alright, A and its complement becomes 0, B and its complement becomes 0, in the sense we don't have this, so we will be left with A bar B bar plus AB. We started with this, we will be ending with this. So whenever we come across this one, we can plug in with this one. Alright, this is the proof. This is the one. We have to, there is a substitution, like to reduce the circuit. There is one method, like, yeah. And the full subtractor has 3 inputs, A, B and Bn, the third input, and the final difference and the final borrow. Alright, so what are the combination, guys? Intentionally I left some place over here. Alright, it's like divide and conquer, it will be easier. What we have is A minus B minus Bn, isn't it? Hold on, understand the operation between A minus B, have the difference, have the borrow, and then go for minus Bn. That's what we can do, like that's more easier to understand. So that truth table we have, intentionally, guys, intentionally I left this place. All right, I got this separation intentionally for divide and conquer. It will be more easy. Understand A minus B, we have some result, then that result minus Bn, we have the final results. All right, so guys, A minus B, going for A minus B, A minus B over here. Let's see what will be the difference and what will be the borrow. 0 0, we don't need any, like the difference is 0, and this let me go for another color, okay, so that it's the saying that it's the intermediate operation, only between A and B. 0 minus 0, the difference is 0, and we don't have any borrow in this case. 0 minus 0, the difference is 0, and still we don't need any borrow. That operation between A minus B, only for A minus B. And yeah, that troublesome confusing combination, 0 minus 1, we have a difference 1, and also this operation needs a borrow. All right, it's a 0 minus 1. Once again we have a difference of 1 with a borrow 1. 1 minus 0, we have the difference being 1, and we don't need any borrow for this one. 1 minus 0, 1, because this difference is 0 and we don't need any borrow. 1 minus 1, the difference is 0 and no borrow needed. 1 minus 1, the difference is 0 and we don't need any borrow, even that will be 0. Now this is the result for A minus B, and this is the borrow. Let's check. Let's go for the second half. This is the first half, let's go for the second half. In the sense A minus B, we have this one minus Bn. In the sense we'll have to go for 0 minus 0. Why? Because A minus B is this one minus Bn. 0 minus 0, the difference is 0, the final difference is 0. Even during this operation we don't need a borrow, and so previously we no borrow, so entire we don't have a borrow. And 0 minus 1, 0 minus 1, 0 minus 1, the troublesome subtraction. 0 minus 1, we have a difference of 1 with a borrow 1. Previously we didn't have a borrow, now we have a borrow. 0 minus 0 didn't have any borrow, but 0 minus 1 we have a borrow. And the next one, 1 minus 0, 1 minus 0, the difference is 1 and we don't need a borrow in this case, but previously we have a borrow. This is to be understood over here. 0 minus 1, the difference is 1 and the borrow is also 1 in this case. Now that's for a minus b. Now we are going for a minus b minus bn, in the sense 1 minus 0. 1 minus 0, the difference is 0. We don't need any borrow in this case, but previously we had a borrow, so that has to be taken forward over here. That cannot be neglected, the previous borrow, a minus b. Once again, alright, so here 1 minus 1, the difference is 0. We don't need any borrow, but the previous operation has got a borrow, and that will be carried forward. And once again, 1 minus 0, the difference is 1, the difference is 1, and 1 minus 0, we don't need a borrow in this case, and previously also we didn't have any borrow, now it's a 0. And here 1 minus 1, 1 minus 1, the difference is 0, and no borrow in this case, previously also no borrow, and so it's a 0. And 0 minus 0, the difference is 0, no borrow, it's a 0. Previously also we don't have a borrow. And 0 minus 1, it's a 0 minus 1, the difference is 1. Do we have a borrow in this case? Yes, we have a borrow, previously no borrow, so entire 1 minus 1 minus 1 has a borrow. 0 minus 1 has a borrow, and this is the, now guys, if we check properly, this is not needed. This is the intermediate stage, a minus b, and now this is the final truth table. This will be the final truth table. Check it. A minus b in, the difference is this one, 1 2 3 4 and 1 2 3 4. I'm cross checking it. All right, this is the one. This will be the final truth table for a full subtract. This is how we understand. And once again, difference for the difference circuit in terms of a, b, bn. So once again, going for a 3 variable k map, so for the difference, in terms of, what do we have for difference in terms of for difference we have a, b, bn, we have a 0 0, 0 1, 1 1 and 1 0. We have a 0 1 over here. Now let's check for the difference, for what values of for what combination of a, b, b and d has the difference has got 1. All right, so this is the first one, 1. For 0 0 1 combination, 0 0 1 combination, we have a 1. We are done with this one. And another one comes at 0 1 0, 0 1 0, we have a 1 over here. We are done with this one. Another one at 1 0 0, 1 0 0, we have a 1, this one. And another one at 1 1 1, another one at 1 1 1 over here. So there isn't any possibility for reduction, there isn't any possibility. So straight away difference D, this cell gives 0 0 1 plus this gives 0 1 0 plus this gives 1 0 0 plus this gives 1 1 1 in terms of a, b, bn. Now this one will be a bar, b bar, bn plus this will be a bar, b, bn bar because of this one plus a, b bar, bn bar plus a, b, bn. Guys, a small simplification over here, taking out bn as common from two terms, bn as common from this one over here and over here. What do we have? We have A bar B bar plus AB. From here, A bar B bar plus AB from these two terms, plus, when taking out B in as common, plus, and taking out B in bar as common, B in bar from this one and this one, what do we have? A bar B plus A B bar. So this is the expression for D, and so that we can erase this one, the K map. For I need the place for difference D, the difference D here, this is A exclusive NOR B into Bn plus this one A exclusive OR B into Bn bar, A exclusive OR B into Bn bar. So guys, this can be making use of this one. So this can be, this A exclusive NOR B over here can be written as A exclusive OR B, it's a bar. Now this one, like this bar something, that's like, now this one exclusive OR operation between this term and Bn. Alright, so finally the result would be for the difference A exclusive OR B exclusive OR C. Now this is the expression for the difference, exclusive OR operation between A exclusive B and Bn. So that's it, that's the final one. Now K map simplification for the Borrow, for the Borrow to implement the full subtractor. In that case, to avoid confusion, I am erasing this one away. Only for the Borrow, it's only for the Borrow. Once again for Borrow, alright, for the Borrow, this one, the K map in terms of A, B, Bn, in terms of A over here, B and Bn over this side, 0, 0, 0, 1, 1, 1, 1, 0, it's a 1, 0, and for A it's a 0 and 1. Checking for what combinations of A and B, we have 1 for the Borrow. 1 appears over here. For which combination is this? 0, 0, 1. 0, 0, 1, we have a 1 for the Borrow, and we have a 1 for 0, 0, 1 combination. Here this one, 0, 0, 1 combination, we have a 1, and this one for 0, 1, 0, 0, 1, 0, it's over here, 0, 1, 0, and 1 for 0, 1, 1, 0, 1, 1, we have a 1. And the last and final 1 for 1, 1, 1 combination. 1, 1, 1 combination is this cell, and we have a 1 over here. So in that case, we don't need this truth table anymore. Why? Because we have that K map, and from the K map it's just reduction and then implementing the full subtractor, making use of two half subtractors. The picture should be reflecting in the same manner, then only it's accepted. So now this combination, which combination, guys? This combination gives, we are trying for Borrow, isn't it? Evaluating for Borrow. So Borrow, that gives for Borrow this one 0, 0, 1 and 0, 1, 1, 0, 1, 1 plus this. We are done with this combination. All right, another combination is this one. Another combination is this one, which gives us, this cell gives 0, 1, 1, 0, 1, 1, and this gives 0, 1, 0, 0, 1, 0 plus. And we are done with this combination. We have another combination, these two, which gives us this 0, 1, 1, and this is 1, 1, 1. So which will be redundant over here, this one, this gets eliminated, this one, 0 and 1. And so finally we have A bar Bn, B got redundant over here, A B Bn in that case, plus, and over here this gets away, this one 1, 0, there is a change over here, that gets reduced, and it's a A bar B, the third term got reduced over here, and this one A gets eliminated, plus B Bn is left over here. That's the reduction over there. And guys, we are trying for the borrow. All right, we are trying for the borrow, and a not touching that a bar b, this one, plus a bar b in also as it is, plus b in is multiplied with a 1. We can assume that there is a multiplication with this over this side, assuming this to be, we have a into 1, and that according to Boolean, one of the Boolean algebra, this can be over here, this 1 can be plugged in with a plus a bar, a plus a and its complement, that will be 1, or operation between these two. All right, so one of the Boolean algebra, a minus a bar b as it is, and a bar b in also as it is, plus simple multiplication a b in plus a bar b into b in. Guys, taking out a bar b from here and a bar b from here, what we have is a bar b, taking out a bar b from here, it's a 1 plus b in, 1 plus b in, plus what, a b in from here, and what we have is a bar b in. All right, so once again, now the Boolean reduction over here is 1 plus b in will be or operation, 1 plus anything, that will be 1. So we have a 1 over here, it's a bar b as it is, this becomes 1 plus a b in plus a bar b in is multiplied with a 1 that can be plugged in with, which can be plugged in with b plus b bar. We have done the operation with a plus a bar. Now the second, it's a b plus b bar, it's a bar b plus a b in plus simple multiplication over here, a bar b plus, sorry, a bar b into b in plus a bar b in, simple multiplication over here. All right, once again taking out a bar b as common from here and here, so a bar b, taking out a bar b as common from these two terms, so a bar has come out, we have 1 plus, and from here it's a b in. All right, and taking out something else can be taken out as common, b in bar can be taken out as common from here and here also, b in, yeah, of course, b in can be taken out as common from this one and this one. So here we have a b plus here we have a bar b bar. All right, this becomes 1 into this one, this entire inside the braces becomes 1, this becomes 1, and the final for the borrow circuit, for the borrow, the expression will be, for the borrow, the expression will be, guys, this one, it's a 1, this part is 1, we have a bar b plus, this is a exclusive nor b into b in, and now this can be a exclusive or b plus, this can be plugged in with a exclusive or b bar b in. We came across this substitution twice during this operation. All right, so remember that is the prerequisite while designing a full subtractor, making use of two half subtractors. We have that AOI logic, that's different case, but general always repeated task is to implement a full subtractor making use of two half subtractors. And these are the two equations, difference for the difference and a borrow. And as said previously, we have three inputs, A and a B, and somewhere we have that B in. All right, so exclusive OR operation between AB gives A exclusive OR B. But still, for difference, we have this part exclusive OR C, or guys, it's previously it should be Bn. I'm sorry, it is it's a Bn previously. All right. So we have Bn over here, taking this input, and once again XOR operation over here. XOR operation over here will give us a exclusive OR B from this side, and here exclusive OR Bn, which gives us a difference, the full subtractor difference for the full subtractor. We have this one, so we need to go for this one. In the sense, the input to the exclusive OR gate should be ANDed. In the sense, taking out over here, and a NOT gate over here. NOT gate will give us, and B. We will have over here. We will have if you have a AND gate over here, the output is A bar B, which is this. All right. And how to obtain this one? We similar as we have taken an output and we gave to NOT gate. The same way we take out an output from this one. We take out an output from this one. Let me go with the black one. This one, take it out. All right, take it out and NOT it. Take it out and NOT it, which gives us this one, the NOT of this one, and multiplied with Bn. Take out that Bn. This is our Bn. See, this is our Bn, and give it to what operation? AND operation between this one. So this one, AND operation between this one. Can you see the similarity? This is a combination of exclusive OR gate, AND gate, NOT gate. Exclusive OR gate, AND gate, NOT gate. This one half. This is half subtractor. This is another half subtractor. And from here we have what do we have? We have from here it's a bar B, and then giving this input to OR gate, and this output will be this one, giving us the borrow over here. It's a bar B from this side, and the output will be this plus this one. Here we have exclusive OR B, its complement multiplied with B in exclusive OR, it's a complement, and from here we have a B in, and this is the final expression for B, and this is implementing the full subtractor, making use of two half subtractors.